How to derive the system of algebraic equations from the mathematical model. In the finite volume method, this is done using the integral form of the governing equations rather than the differential form. So if we looked at conservation of mass, that's a differential form, and the equivalent integral form is shown over here, and that integral is applies to any particular any arbitrary controls volume within the flow domain. And this just states that the net volume flow out of any arbitrary control volume has to be 0. Similarly, for conservation of momentum, there's a differential form and the equivalent integral form, and it's the integral form that the finite volume method uses. And armed with the integral form, we apply mass and momentum conservation to each cell. If we go back to our particular example, and let's consider this cell over here, and we do a control volume balance for this cell. Let's say we do that for mass conservation, so that's the integral form of mass conservation. And so we need to know what is the net volume flow out of that that cell. And let's ignore the equation right now and just do this based on physical argument. So we want to know what is the volume flow, the rate of volume flow out of each of these segments of the control surface. Let's take a look at this particular segment. Okay. Now I need to know what the velocity is over there to figure out what is the volume of flow going out. I'll assume that the velocity along this segment of the control surface is constant and is equal to the value at the midpoint. Okay, so I'm doing averaging here, and I'm introducing an error in the process. And this value is not calculated directly, so we have to use an interpolation between the cell center values. So we just interpolate these two cell center values to get that. So when I write the volume flow contribution from this particular boundary, it will involve the velocity here, particularly the u velocity, and the u velocity there. Then I go and take a look at the volume of flow going out of that boundary, and that is that's no slip, so there's no volume flow going out of there, which means that if I was doing it through the integral, then there's no contribution to the integral. Whereas when we do this, when we calculate the integral, we will interpolate between this value and this value. So you can either do it based on physical arguments, or you can go back to the integral, and for simple problems you will get the same result. And that's the nice thing about the finite volume method, that it's very physical, and so I find it relatively straightforward to understand the big idea of it. When I'm at this boundary, I know what the velocity is from the boundary condition, so again I can calculate what the volume of flow is from the boundary condition, and so on. So I add up these 4 contributions and set it to 0, and that's my algebraic equation for mass conservation. Similarly, I have to do it for x momentum and y momentum, so I'll get 3 discrete or algebraic equations per cell, and I'll have a total of 36 equations because I have 12 cells. So 36 equations, 36 unknowns. So one has to average and interpolate cell center values to get values at the control surfaces, or these are called faces in the method. Okay, and we introduce an error because of the averaging and interpolation, and it's very important now what's that level of error introduced, and we will take a look at that later. And at the boundaries we use boundary conditions, and we will work through an example to get a better idea of how this works.